Good morning, everybody, and welcome to this webinar, which has been organised by the Northwest region and Noel Hensman on behalf of the process industries for IMechE. Today, we're going to hear about actions for the engineering profession from COP26, where Dr. Tim Fox will be discussing the implications of COP26 for our engineering profession, how we should respond, and our priority areas for action. I'll be moderating today. My name is John Clegg. I have about 30 years in the oil and gas industry, and more recently looking at renewable energy, including geothermal, where I'm currently acting as CTO for a new geothermal company, Hephae Energy Technology. Dr. Tim Fox is an internationally recognized expert in climate change mitigation and adaptation, with specialist knowledge of clean energy systems, sustainable cooling, sea level rise, sustainable food systems, and the process industries. He works as an independent consultant operating at the intersection of science, engineering, policy, business, and communications, and he's a COP veteran. Tim's a chartered engineer, and he's a fellow of the IMechE, where he chairs the Climate Change Adaptation Working Group. He's the immediate past chair of the Process Industries Division Board, and he represents the IMechE on the UK Infrastructure Operators Adaptation Forum, the IOAF. Tim has been the author of numerous peer-reviewed papers, research reports, thought leadership reports, and policy papers, and we've seen him in hundreds of press articles, op-ed pieces, broadcast media appearances, conferences, and webinars. Before I hand over to Tim, I'd like to remind the audience that we will be taking questions at the end of this, and there is an attendee Q&A tab that should be visible on your screen as you watch the webinar. So please start questions coming in as soon as they come to you. We will take them, as many as we can, immediately after the presentation. But with that, I'm going to hand over to Tim. And Tim, please go ahead and start the presentation.
Thank you very much, John. And thank you very much to Noel for setting this up. It's a real pleasure to be with you. I'll just pull up my slides. And so John gave a fairly comprehensive statement around my background and my role within IMechE. So the main points to make here are that I'm indeed the immediate past chair of the Process Industries Division Board, and much of what I'll be discussing this morning is highly relevant to the process industries. So hopefully that'll become clear as we make our way through the morning. So what I want to do is start off by giving us some background to the UNFCCC process and indeed the COP activity and the process around that. Some of you will be familiar with this, and I guess many of you may not fully appreciate what these acronyms mean. So let's just take a dive into the history of the UNFCCC and COP and the journey so far, just to bring us to the same point in understanding of what this process is all about. So the United Nations Framework Convention on Climate Change, the UNFCCC, was established in 1992. So back then, as a result of a number of studies that had taken place, it was becoming clear that there was potential for humans to significantly disrupt the global climate system. And the UNFCCC was set up to combat what were considered then to be dangerous levels of human interference in the climate system. And it was established at in Rio in 1992 at what was known as the Earth Summit, which was a major meeting of governments from around the world to consider the much broader issue of environmental impact and sustainability, but within that was the consideration of climate change. So that's where it all began, and the Conference of the Parties, or what has become known as in acronym terms as the COP, is essentially what it says on the tin. It's a coming together of the signatories to the convention alongside other interested parties. So observers from civil society, groups that have an interest in climate change, and a much broader, wider range of the of public interest groups. But at the core of the COP process is a negotiation between governments around what sort of action should be taken to ensure that we do not push the Earth system into a dangerous state for human beings. And the negotiations take place within a fairly close-knit community of global nations, and then the rest of the activity around COP takes place within more sort of public fora. So if we then sort of fast forward a bit to 1997, the first major output of this process was what many of you will have recall as being the Kyoto Protocol, which was the first attempt at trying to put in place some sort of mechanism to enable us to come together to reduce emissions fairly and equitably distributed across the polluting nations of the world. And to some degree, it achieved some success. There were some reductions, but there were significant challenges associated with the failure of some significant polluters to sign up to the protocol, indeed for their national governments to ratify their signatures on the protocol. So that was the initial process, and it was a process in which, or a mechanism, I should say, in which there was an attempt at trying to place responsibility for emissions on the largest emitters, and indeed not just the largest emitters in real time, but the largest emitters historically. We don't want to dig too far into that at the moment, because that's quite a lengthy process. It's a very detailed process, and really it just sets the scene for the meeting in Paris, which took place in 2015, which was COP21, at which we made a significant step forward, really, in terms of the COP process. So at that meeting, there was a strong commitment, a strong desire to ensure that we could keep global mean temperature rise relative to pre-industrial to 2 degrees C or less. A strong recognition that exceeding that temperature could lead to catastrophic consequences for many nations in the world, and a significant impact on a very large portion of humanity. Not to forget, of course, the impact on ecosystems and the natural world. And in fact, there was an aspiration at Paris, which was pushed strongly towards the end of the meeting, to try to limit the global warming to a temperature rise of 1.5 degrees C relative to pre-industrial. And that really was a significant step. And that raised the level of ambition amongst nations attending the meeting. And subsequently, that has become a really significant part in the process. And we'll come back to that when we discuss the outcomes from COP26 in Glasgow. And indeed, at COP26 in Glasgow, which is the most recent conference of the parties, back in at the back end of November, beginning of December, it was agreed that the Glasgow Climate Pact would be the outcome of that conference, and I'll come back to that in a moment. So, just before we dive into what happened at Glasgow and what the implications are for engineering, let's look at the context within which all of this and the decision making around our approach to climate is embedded. The context really for what we're talking about this morning, and the context is really set a few months ahead of the COP by the IPCC's publication of its physical science basis chapter of the sixth assessment report. So the International Intergovernmental Panel on Climate Change, which was set up alongside the UNFCCC process, effectively to do the science and to inform policymakers and a broader community as to what the state of the climate was or is and where it's going. And the first thing, let's have a look at where we are now in terms of the output of that most recent report. There are a number of statements in there and a number of findings in there that are really fundamental to the way we think about climate now and really show us the length of the journey that we've been on so far. This was the first time really where the IPCC had come out with a categoric statement that it is unequivocal that human influence has warmed the atmosphere, ocean, and land, and that certainly humans are at the core of the changing climate, in addition to, of course, the influence of natural processes. And indeed, some of the evidence presented in the report was really quite sobering. So for each of the last 4 decades, each decade has been successively warmer than the preceding decade. And that is really quite significant. So as we've gone into the latter end of the 20th century and into the 21st century, the climate change signal in terms of the global warming that is being measured and monitored has become quite significant compared with decades previous to that. Now, one of the key findings was that the global mean surface temperature has already risen by 1.09 degrees C, so effectively 1 degree higher than in the most recent decadal period under consideration, which is 2011 to 2020, relative to the immediate sort of mid-industrial period of 1850 to 1900. And in fact, there's been larger increase in temperatures over land than over the oceans. And of course, this is quite significant that a 1 degree rise already is having an impact on the climate. And we see this in terms of widespread and rapid changes, both in the atmosphere and the ocean, and in the cryosphere, which is the ice on the planet, and the biosphere, which is the organic material within the planet, so the trees and vegetation. And a couple of key points there. So globally, we have seen average precipitation over land increase since the 1950s, and its frequency and intensity is increasing. Of course, we're very cognizant of that in the UK with increased flooding, and across Europe with increased flooding, and not only the frequency of that flooding, but the intensity of the rainfall causing that flooding. Climate zones and mid-latitude storm tracks have shifted poleward in both hemispheres, the northern and southern hemisphere. So this is an indication that climate zones are on the move. So areas are experiencing climate that was only previously experienced closer to the equator previously. So in the UK, we're slowly moving towards a climate that is more familiar to those in southern Europe. The global proportion of Category 3 and 5 tropical storms has increased significantly during the 1980 to the 2020 observation period. Heat is becoming more of a problem. Heat extremes have become more frequent and intense. And very significantly for future flooding and sea level rise, we are seeing global glaciers and ice sheets in retreat. And of course, in terms of impact on other areas of natural processes like ocean circulation and indeed albedo effects at the North Pole, we're seeing the Arctic sea ice area decrease significantly. So that's a sort of state of play today. We're seeing sea level rise accelerate. And the question then is, well, what sort of direction are we traveling in? Well, again, very sobering. The physical science basis of the sixth assessment report told us that we could expect significant changes into the future, regardless of which scenario we look at. So this is really important, I think, to understand. So particularly, as us as engineers looking at our infrastructure and our built environment, if we just look at the basic numbers, then compared with 1850 to 1900, that sort of early to mid-industrialization period that we look back to in terms of seeing how we are progressing with climate change. If we look forward to the end of this century, it's very likely that mean surface temperatures, global mean surface temperatures, will under the following sort of three scenarios have the kind of numbers associated with them on the slide. So I won't go through those, but the key issue to understand is that with these emissions scenarios, certainly the very high scenario is an untenable position for us as humans on the planet. And the low emissions scenario, which assumes that we make progress towards net zero, is still quite challenging. So what we have to understand is that regardless of which scenario we take, and even if we as engineers are successful in helping society transition to net zero by 2050, global mean surface temperature of 1.5 degrees C will be exceeded at some point in our journey towards that net zero outcome. So this is really important when we come on to talk about adaptation, and I'll come back to that later. So in the very low greenhouse gas emissions scenario, which assumes that we make progress towards net zero by 2050, we will exceed that 1.5 degree Paris aspiration, but indeed we will come back down towards the end of the century and end up somewhere closer to 1 degree C. Now, the issue is, of course, that we don't know exactly how the climate will respond to such an upward and then downward moving global mean temperature. And that's really important to us when we think about adaptation. But I guess the key point that I want to make here is that many changes in the climate system are now baked in to occur, and that those changes become larger in direct relation to increasing global warming. So increased frequency and intensity of hot extremes, heavier precipitation, and more frequent and intense droughts, and significant changes in the ice cover on the planet. So some of these changes are going to be irreversible for centuries or millennia to come, especially if we're thinking about oceans, ice sheets, and sea level rise. And indeed, the most recent IPCC report in terms of sea level rise made a fairly bullish statement in that although under the worst case, very high emission scenario, we expect something like a 0.63 meter to 1 meter rise in global mean sea level rise, the IPCC could not rule out a rise approaching 2 meters by the end of the century and possibly 5 meters by the end of next century under a very high emission scenario due to the uncertainty in ice sheet processes in Antarctica. So we really need to be cognizant that sea level rise could, in a very low probability but very high impact scenario, end up with a significant challenge for us as engineers in terms of coastal infrastructure and industrial assets on the coast. Having set that context, let's have a look at the outcomes from Glasgow, and let's take an engineering perspective on these outcomes. So I've drawn out, there were a large number of outcomes from Glasgow, but I've drawn out here the key outcomes that have relevance to us as an engineering community, and I'm going to address some of these in more detail during the second part of my talk. So the most significant outcome really in terms of emissions reduction, so what's known as mitigation, was that the Glasgow conference, COP26, was set to review the national determined contributions that had been set in Paris. So the process is that every 5 years, these NDCs, so this is really the commitment that countries have made to reduce emissions on a voluntary basis, are reviewed. And at Glasgow, it was determined that the current those NDCs that were put on the table at Glasgow were currently projecting us to head somewhere towards a 2.4 degrees C outcome this century for global warming, and that was really considered to be unacceptable. And so countries have been asked to come back in 2022 with more ambition, so as to define a set of NDCs globally that enable us to transition to reaching that 1.5 degrees C Paris commitment. Now, what was really important at Glasgow was that 1.5 degrees became the normal topic of conversation. So what had been a high level extended aspirational goal at Paris has now become the norm, which is a really significant step forward. So the conversation is around 1.5 degrees C now, not 2 degrees. And this increased commitment by coming back within a year instead of in another 5 years, which is what would have been within the normal UNFCCC process after Paris, is quite a significant step. And this increases the level of ambition around transitioning to net zero, which of course has a significant impact for us as engineers. It was also agreed to phase down unabated coal, which is significant for us as engineers working in the process and energy industries, and the phase out of inefficient fossil fuel subsidies. Now, you will have seen a lot of press coverage that tries to downplay the importance of these announcements, but these were significant announcements. And the fact that India was sort of called out towards the end of the process because it refused to agree to a complete phase out of unabated coal as opposed to a phase down, I think was significantly unjust, because as many of us know, India is a rapidly developing nation, as indeed is China and a number of other nations in that area of the world. And they have very high dependence on coal with no natural gas and oil resources of any significance of their own. And their populations are growing significantly. So to ask them to phase out unabated coal was a little bit unfair. And phase down is a significant step forward. And we as engineers understand the challenge of making that transition from a coal-based system to a clean energy system. But India has set a target of reaching net zero by 2070, and given the size of the country, that is a significant contribution. The other thing that many of you will have noticed from an engineering perspective was the announcement that 23 countries and 39 cities, states, and regions had committed to moving towards 100% zero emissions car and van sales by 2040. And you're probably aware that our own government here in the UK has committed, made significant commitments in line with that, and indeed committed to have non-zero emissions heavy goods vehicles, for example, phased out by 2040, smaller weight vehicles by less than 26 tons by 2035. And you'll all be aware of the announcements around car and vans on a similar sort of timescale. That has significant implications for us as engineers and within the process industries, of course, providing much of the infrastructure that provides fuels for these vehicles. That has significant impacts for the priorities in our sector and sectors moving forward. There was also a strong recognition of the need for a just transition. And I think this is particularly pertinent to the process industries, where many of our colleagues are involved in working in areas of technology and fuel supply, etc., that are transitioning through to clean energy technologies. And it's really important that the workers and communities affected by that shift to low carbon systems are treated justly in that transition. Taking a fair approach to making that transition for our workforces. Two more announcements that I want to focus a little bit more strongly on during the course of this morning are the announcement that 103 countries had signed up to the Global Methane Pledge, which is really significant and is looking to reduce global methane emissions by 30% relative to 2020 by 2030. And that is a hugely ambitious target from an engineering perspective, but we'll come on to discussing how we prioritize that. And the other area of significance was that rich countries had agreed to at least double the funds to poor developing countries for adaptation action. And at the moment, financing for adaptation only represents about 25% of financing flows. So I'm going to concentrate for a little bit on the Global Methane Pledge and the adaptation element, because I think those are areas that do not get the airtime that they would justify. And we'll come back to the broader net zero question in a moment. So methane, as many of you know, is a potent greenhouse gas. It has a global warming potential about 80 times more powerful than carbon dioxide on a 20-year time span. And what this means is that by having an effect on methane, we can have a very rapid and immediate effect on global warming. So it's a very useful approach to reducing methane emissions is a very useful approach to mitigating climate change in the short term. And in fact, Inger Andersen, the executive director of the UNEP, recently said that cutting methane is the strongest lever we have to slow climate change over the next 25 years. And let's just return to the IPCC sixth assessment report and the physical science basis, and you'll see here a number of statements that about methane that make it very clear that methane has already been responsible for about half of global warming. So remember, I said we'd had 1 degree of global warming. Well, half a degree of that global warming has been identified as accountable to methane emissions, and the sustained mitigation of methane emissions was regarded by the IPCC as a standout option for near and longer term gains on surface temperature with high confidence. But it also leads to other benefits, environmental benefits and health benefits around air quality and by reducing surface ozone levels globally. So we'll come back to that in a moment. So there's a very strong case for abatement of methane emissions. And indeed, the background to the pledge was that the pledge was established between the EU and the US in September of last year, ahead of COP26, basically building on the EU's methane strategy, which had been in development for a couple of years. And really, it took this forward as a EU-US initiative, and raised 103 signatories by the time we got to COP26, where it was officially and formally launched. Now, by reducing global methane emissions by 30% by 2030 relative to the 2020 value, the significance of this as a potential mechanism for tackling mitigating climate change cannot be underestimated, because it's been calculated that that would have a similar impact on global warming as switching all the world's cars, trucks, ships, and planes, the entire global transport system, to net zero emissions technologies over the same time frame. So that puts the scale of the prize to be gained into perspective. And delivering the pledge would reduce warming by at least 0.2 degrees C by 2050, which is a significant help in getting us towards that 1.5 degree target. So let's just have a quick look at where those global methane emissions come from. Around 60% of total global methane emissions come from human-related activity. The balance, the remaining 40% come from natural activity, and those natural sources are methane emissions primarily from wetlands, permafrost, and wildfires. If we look at human anthropogenic methane emissions, agriculture is the largest contributor. It accounts for about 40%, primarily livestock farming, which is about 32%, and rice is about the balance at about 8%, rice growing. Fossil fuel operations within the process industries account for around 35%, so a little bit less than agriculture. And this was primarily from the oil and gas industry, around 23%. And coal mining is responsible for the balance of 12%. That's largely from off-gassing from unsealed mines and open mining activity. Waste management, which is a bit of a surprise probably to many of you, accounts for around 20% of global methane emissions, and that's primarily from organic material like food waste in landfills, off-gassing methane as it decays, and wastewater processing in sewage works, sewage farms, etc. So many of these areas are process industry related, and indeed it will probably come as a surprise that bioenergy production itself, which is a net zero emissions solutions activity, is in itself responsible for around 5% of global methane emissions, and that's largely from leaking from bioenergy plant. So let's just focus on the process industry. So the sources of these methane emissions, what are known as fugitive methane emissions, are largely from leakage within the system. So the upstream and downstream oil and gas industry, leakage primarily along the production and supply and distribution chain. So this is just leaking equipment within those sections of our oil and gas activities. Non-emergency venting and flaring of methane during the oil and gas activity, and abandoned wells that haven't been correctly sealed or not robustly sealed. As I mentioned, the bioenergy sector is responsible for a leakage from AD plant, from biogas upgrading plant that are producing biomethane, and the gas distribution network, and venting from storage tanks where methane is contained, particularly liquid methane at cryogenic temperatures, and venting for pressure relief from those tanks. The food system, I already mentioned, livestock farming, enteric emissions, so that's the emissions from the animals themselves, is responsible for about 70% of the emissions, and the manure management, so slurry management, etc., responsible for around 30% of livestock farming's contribution, agriculture's contribution. And wastewater, as I said, leakage from sewage handling plants. So a lot in the process industries for us to look at. And recently, the UN Environmental Programme undertook a multi-sector study of the benefits and costs of mitigating methane emissions, and found that actually available targeted measures could reduce emissions by 45% by 2030. So, we understand what we need to do. We understand how to tackle these leakages and these venting problems. And the key action and priority for us out of this is to actually translate that knowledge and know-how into action within the field. And in fact, the next question is, well, how much is all this going to cost? Well, actually around 60% of the available abatement measures actually have low cost, and around 50% of those are better than zero cost. And that's because the methane is so valuable within itself that by tightening up on methane leakage, we actually increase the amount of product that is reaching the marketplace, and therefore we cover the cost and some in terms of that abatement. Of course, it has additional tackling methane as the UN environmental program identified, has significant other benefits around related to air quality due to that ground level ozone. And in fact, if we look at the oil and gas and coal sector specifically within the processing industries, the International Energy Agency has published a lot of reports and data in the past couple of years that shows there's considerable scope for cost-effective actions to deliver methane emissions reductions from this sector, with practical measures available that could achieve a 75% cut by 2030. And indeed, again, these could largely be achieved at low cost or zero cost. And the IEA is very busy creating lots of tools to help us as engineers do that. So key thing is, what are the priorities in this area? Well, we need policy and regulatory action, clearly. And we will see policy and regulatory action in response to that Global Methane Pledge. But of course, there's a lot of scope for voluntary industrial initiatives and improvements in how we monitor, report fugitive methane emissions, and a lot of scope for transparency in the data associated with that. And those policy and regulatory tools might look like leak detection and repair requirements, technology standards, bans on flaring, non-emergency flaring and venting, and market interventions to remove barriers to using captured fugitive methane and making it profitable to do so. That's really important. So encouraging organizations to capture that methane and to utilize it and take it out of the climate system. Further developments required in the technologies, particularly satellite-based technologies that enable us to underpin those frameworks for measuring and reporting. And of course, as engineers, we need to create practical solutions to preventing those leaks, but also to really prioritize creating high-value utilization products from that methane that we capture. And there's a big role for us in creating commercial opportunities for methane capture and use. So turning now to the theme of adaptation. So the COP26 presidency theme, they had a number of themes. There were 4 themes associated with COP26. And one of the key themes was around adaptation and resilience. And I'm just going to focus on this for the final part of my, my talk. So adaptation is all around adapting our built environment and infrastructure and systems to cope with the climate change that is going to occur regardless of what we do with emissions reduction, and indeed as a result of the emissions that we will make in that journey to an emissions reduction, ideally towards net zero. So the climate will change. It is changing. It will change, and there is a need to adapt to that, and that was recognized within the COP26 process, and that is significant as the level of interest in adaptation and emphasis on adaptation is increasing within the COP process from a point a decade or so ago when adaptation was really taboo to discuss and even discuss within the COP process. A key here, of course, is that there are vulnerable nations around the world that are potentially significantly impacted by climate change, and indeed already being impacted in climate change. And it's really important that solutions that we as engineers bring forward, affordable, safe and robust solutions for those communities to be able to apply. And indeed, the Climate Vulnerable Forum and the Vulnerable 20 Group, which is the 48 most vulnerable economies in the world, have been demanding an increase in the level of focus on adaptation and adaptation funding. So I'm going to focus on 2 areas that are, have very significant global application in terms of responding to climate change. So the response to increased heat and the response to the increased frequency and intensity of flooding. So heat has a significant impact not only on us as individuals in our homes, but also in the workplace and of course within the process industries. And home and workplace issues to consider are things like discomfort, sleep deprivation, food safety, cognitive thinking ability is impaired by heat, productivity, and indeed the frequency of accidents, which of course is really important for us within the process industries, and the morale of both our workforce colleagues and indeed our families and friends. So heat is a real challenge, not only to equipment but to people. And as we move forward, the impact of heat is going to increase not only in intensity but also in frequency. And if we continue to meet that challenge through business as usual sort of systems like air conditioning systems, we're going to see a significant increase in the demand for energy and a significant increase in as a result in emissions from greenhouse gases from those systems. And in fact, air conditioning systems are very challenging in a number of ways, in that they not only produce greenhouse gas emissions from the fossil fuel-based power systems that many of them rely on still around the world, but greenhouse gas emissions from leakage of high global warming refrigerants is significant. And there are issues associated with the sustainability of manufacturing operation and end-of-life disposal that have impact not only on the carbon footprint of those systems, but also the broader sustainability of those systems. And challenges for us within the process engineering sector, more specifically, arise around the ambient external temperatures that many of our air-cooled heat exchangers and other heat exchangers are going to have to work within. Higher temperatures of the cooling fluids that are supplied to the heat exchangers, and this could lead to overheating of plant, feedstock, and the product. And in fact, the recent experience in the northwestern United States and Western Canada during last summer, when the heat dome effect caused significant temperature extremes within that area on process industries, is something that we can draw many lessons from. And if we're going to adapt to this kind of heat, then, as I've implied in the last few minutes, we need to do that in a way that is sustainable and also achieves net zero while we're delivering cooling. So to deliver sustainable net zero cooling, we need to think about things like demand mitigation, so reduction in the demand for cooling in the first place, use of natural resources, increased energy efficiency, circular economy design principles, before we start to reach for carbon offsets to try to mitigate the effect of our emissions in those areas. So there's a lot of work for us as engineers, a lot of priorities within there for us to improve the way in which we provide cooling, to move us away from those fossil fuel-based and unsustainable approaches to cooling. Turning finally to flooding. Increased flooding is a challenge globally in the currently and in the decades ahead. And flooding, both in terms of internal flooding and coastal flooding, is set to increase as we go forward. And as engineers, we need to be thinking about designing for extreme flood events where a number of characteristics come together to produce significant flooding events, such as when we've had significant rainfall and we have saturated soils within degraded landscapes, and leading to significant levels of runoff, urban planning that has led to significant hard surfaces, leading to heavy runoff. And if those characteristics are in place in a coastal region, then we, in combination with coastal storm surges and sea level rise, we can see really extreme flooding events. And we need to be cognizant of how we design for those and how we respond to flooding. And in terms of responding to flooding, there are a number of avenues available to us. We could build barriers and higher walls, which is a sort of typical engineering approach. But of course, we need to understand that there's only so much we can do in terms of building barriers and higher walls around communities and infrastructure. We can use nature-based solutions, but we have to remember that those solutions will be impacted themselves. The efficiency of those solutions will be impacted themselves by climate change. So we need to be cognizant of that when reaching for those sort of solutions. We can put buildings and infrastructure on stilts, but of course there's a limit to what we can do in that area within the process industries, with our process industries based plants. We could likewise put plants and buildings on tethered pontoons, but of course this also creates challenges around how we get the utilities in and out of those structures. We can make space for water within our sites and within our urban areas that fill with water during times of flooding and act as community spaces or other amenity spaces at times of non-flooding. But of course, we also have to consider abandoning places completely, and there's significant socio-economic challenges associated with that. So just to flag up that there is work going on in this area. It is increasingly becoming prioritized, and to help us in this area, there's work going on around developing standards for dealing with adaptation and how to approach adaptation and how to balance the economic and technical tensions around adaptation. So the desire of engineers to create adaptive solutions, but the economical implications to that and the uncertainties associated with that, leading to questions around the value and benefits of doing that adaptation. And the next step really is to develop significant design codes, engineering design codes that can tackle adaptation at the sort of engineering calculation level within infrastructure and building standards. And indeed, we look to develop the Eurocodes further for climate change adaptation. So there's a need to develop these tools, and for, again, returning to our designer, there's a need to supply the designer with new methodologies and tools that embed these approaches. And very urgently, there's a need for us to look at our infrastructure within that context of passing that 1.5 degree C threshold within the transition to net zero. So we need to be developing outcomes that are adaptive ready, future-proofed, both in terms of new builds and retrofits. And finally, in closing, I just want to say a quick word about the impact of climate change on our work on net zero solutions. So we often think that we only need to consider climate impacts in terms of adaptation, but actually in all the work we do in developing net zero solutions, we have to be cognizant that the climate within which those solutions are going to work is going to change during the lifetime of those technologies, pieces of equipment, pieces of infrastructure. And we need to bear that in mind when we're designing. So in the examples I show here, for example, the hydroelectric scheme, the micro hydroelectric scheme, when we're looking at the potential of that scheme, we need to be designing it to account for the changes in precipitation that will impact on that river that the scheme is working within over its lifetime, both in terms of lower levels in the river and higher in periods of drought and higher levels in periods of extreme rainfall. And if we reach for the carbon offsetting, we have to be cognizant that we can invest heavily in carbon offsetting in forest and woodlands to mitigate our emissions. But of course, as we've seen, there's an increasing trend towards wildfires around the world. And if those forests and woodlands go up in flames, they're not providing a particularly effective mitigation. So finally, just before I open up for questions, what are the post-COP26 priorities for engineers in the engineering profession? Well, the key is that, to meet that 1.5 degrees C 2050 net zero target, we need to double down on engineering for net zero as engineers, and we need to ensure that our solutions are, as I've just said, sustainable, designed for the future climate, and adaptive ready. We need to develop technologies, methodologies, and tools, standards, and codes that help with methane abatement, and indeed new standards, codes, and tools that help with climate change adaptation. And in the case of the latter, they must be based on climate projections and not historical data. We need to ensure that whatever adaptation solutions we bring forward, they're sustainable, they're flexible, they're resilient, they're adaptive ready, and really importantly, in terms of where these adaptations are really urgently needed in developing and least developed economies of the world, we need to take into account local knowledge and technical skills and ensure that, of course, those adaptations are undertaken in a net zero way. So when we pour the concrete, we need to be conscious that that is not necessarily a net zero approach unless we have a eco cement type concrete. So we need to recognize the need for broad collaboration on adaptation with our partners in other disciplines, in socio-economic and political disciplines that affect the context of our work. And we need to develop knowledge transfer, training and skills that's fit for purpose to meet these 21st century engineering challenges. So there I will stop and hand back to John, who will be able to take the questions and answers forward.
Well, thank you, Tim, for a very interesting and very informative discussion. Before I start to relay some of the questions, we've got about 9 minutes remaining of our scheduled time. So there is time for a few questions. If anybody hasn't submitted a question yet, please feel free to do so. Apologies if we don't get to answer them all, but I'll pick what I think are relevant ones. There's a couple that have come in that are quite closely related to each other. And they're two topics that you touched on right at the end of the presentation, just after the questions came in, actually, but they are related. One of them is talking about how we should take a quantitative approach and recognize that, you know, a lot of products that people think of as being net zero actually have significant lifetime emissions, perhaps in manufacture or disposal, or perhaps in, you know, extraction of materials and stuff like that. And there was also a related question about how do we ensure that particularly mitigating and adaptation actions don't actually exacerbate the problem. And you mentioned it yourself at the very end, you know, using more concrete and more steel, for example, to build structures to adapt. Are there any standards that can help us, or any sort of practices that you're aware of that you could explain briefly that could help us grapple with those particular issues?
Yes, John, thanks very much for that question. On the issue of a net zero approach to adaptation, I think, as you've highlighted, I brought that out towards the end of the presentation. And in fact, although there is within current standards around adaptation, which are the ISO standards and the BSI standards, there is a passing references to the fact that, you know, the solutions that are brought forward are sustainable and ideally low carbon. I think, you know, that understanding that in carrying out adaptation activity, in undertaking you know, adaptation, construction, etc., we need to have a sort of net zero approach is relatively new in thinking and hasn't really been fully embedded within the standards and guides that are available for adaptation. So I think that's an area where we need to sort of prioritize articulating that more clearly and building it into standards more clearly. And indeed, likewise, in the other way around, as I pointed out at the end, when we're undertaking net zero designs and looking for net zero solutions, we need to be cognizant that those solutions are going to be working within a very different environment within 20 to 30 years. So if they have a lifetime of a typical engineering plant or asset, we need to be looking at what the climate is going to be like, you know, at that future date and designing for that. So particularly when we're looking at cooling equipment, that is going to have to perform in higher temperatures, or equipment that is likely to be flooded more frequently, particularly with salt water from sea level rise impacts. So yeah, there's a lot of work to be done there, and there's probably a lot of work to be done there also within the sort of education system, in terms of building that thinking into our curriculum within the university and college system. It really should be part of our DNA as engineers to look at things through the lens of adaptation and net zero, and not look at them independently in a sort of siloed way.
Yeah, that makes a lot of sense. And you mentioned education. I'll come back to education in a minute. But at the beginning of the presentation, you were talking about scenarios, and there are a number of organizations who've published potentially climate change scenarios. I know Shell has published some of theirs, because Shell's been pioneering scenario planning for many years. Is there a place for scenarios? I mean, it's very difficult to predict the future, but scenarios makes it easier to do. And is there a place for testing potential mitigation and adaptation strategies against different scenarios? So, will this, it's kind of what you said, will this particular solution work in a 1.8 degree scenario? Will it work in a 2.5 degree scenario, and so on?
Yeah, that's very important, John. So, at the moment, certainly, traditionally, most engineering design methodologies, tools, and codes are based on sort of looking backwards at historical data. So, looking at historical data, so looking at what the climate was like in the past, in terms of the most recent past, and what sort of weather impacts and environmental impacts we might expect on our systems, as historically. So things like a 1 in 100 return rate for flooding, etc., and the number of heat days and number of cool days, etc., cooling days. Sorry, and of course that's all becoming increasingly irrelevant in terms of future design. So the challenge for us then as engineers is, well, there's a lot of uncertainty in how the climate will change, and that uncertainty comes from a number of areas. There's the sort of the physical uncertainty associated with the performance of the climate system itself, the physics. But then there's also the uncertainty around how much we're going to achieve in terms of emissions reduction, and uncertainty around sort of socio-economic and cultural issues around how societies are going to develop around the world during that sort of 20, 30, 40 year time frame. So, when we're looking at our designs, we certainly need to be looking at it through the lens of scenarios, as opposed to just picking single sort of numbers from historical data, which is what we've done in the past. The wind loading factor is this, and we've always used that, and that's the way it is. We need to be looking at a number of scenarios, but what we need to be doing is we need to be considering the sensitivity of our solution to those scenarios. So sensitivity analysis is what is going to become more important. So, it's we can look at scenarios, and we might find that actually for a particular design and performance of a particular design, that under a range of scenarios from low emissions to high emissions, actually the sensitivity of that design is almost, is so low that actually, we can economically design for the worst case scenarios quite easily, but we might at relatively low cost, reasonably affordably, but we might of course find for another widget or a piece of equipment or design, a bit of infrastructure, that it's very highly sensitive to those scenario outcomes. And therefore we have to then start taking a risk-based management approach to how much risk we're willing to how much risk we have appetite for. So the short answer is yes, we need to be getting more sophisticated about our use of scenarios, and we also need to understand more clearly about the uncertainty of the data that is going into those scenarios. So that's really the approach.
Okay, it's almost 12:30. We can run over by a couple of minutes, so there are many questions. I'm just going to pick out a couple. One of them, you talked briefly about education, and the the need to deliver knowledge, training, skills development so that the profession is kind of fit for purpose for what remains of the 21st century, the 80 years that are coming in front of us. Can you share some thoughts on what you think the priorities are for education and how you think education needs to address this and how it needs to prepare new generations of engineers, technologists, and others for this world?
Yeah, thanks, John. That's really important, actually, because obviously the education, not just in terms of undergraduate education and postgraduate, immediate postgraduate education, but more broadly, continuing professional development is really key to ensuring that we've got a profession that is fit for purpose. And there are 3 points I'd like to sort of just bring to the table there, cognizant of time. The first is that clearly this question that we've just been discussing of ensuring that net zero is at the core of our DNA, and that that sits within the context of adaptation and adapting to that future climate is really important. So we should be looking at all of our teaching across those areas, across those different areas of an engineer's journey through his career or her career, should be focused on ensuring that approach is sort of really embedded in our DNA. Then the second thing is that we really need to develop deeper collaborative skills, because these are global problems, and global problems are going to need global solutions. And to get to those global solutions, we're going to have to cooperate globally through global collaboration. And I think it's really important that we develop collaborative skills within the engineering profession, not just across our profession, but our ability to collaborate with other disciplines. So with the legal community, with the social sciences community around behavioral science, with the sort of communities that would be focused on the just transition, so a whole health professionals, a whole range of people that we should be able to collaboratively work with. That's and internationally, so a lot of work to be done there across the entire spectrum of engineering, education, and skills development. And then the third and final piece there that I bring to the table is that we need to be looking at a much more diverse range of people within engineering. So, we need to be attracting a far more diverse group of people into engineering, not just at the sort of undergraduate and college entry stage for technicians and engineers, but more broadly for people to be able to come in to the profession from a mature background from other professions and bring that experience and repackage it to bring into our profession. So, and in that diversity, I mean diversity across the broadest range. So not just gender and ethnicity, etc., but diversity in terms of way of thinking. A lot of these issues are going to need much more empathy with our communities that we work in, and much more diplomatic skills for collaboration, etc., etc. So if we can encourage a much more diverse range of people into engineering, that would help enormously.
That's great. And you probably know I study innovation, and I've written a book and just writing a second book about innovation. And one of the things I discovered in my research and also in my experience, a lot of those things you talked about, in fact, all of those things you talked about, collaboration, working across national boundaries, working with different organizations and different disciplines, and diversity, those are all things that tend to drive successful organizations in not just talking about mitigation and adaptation, but right the way across the whole broad swath of engineering. Organizations that practice that tend to be more successful. So they're good things to do anyway. There'd be additional benefit would come anyway.
Yeah.
We are a few minutes over. One last, there were 3 questions that came in about methane that I thought were kind of interesting. One of them was, if it's so cost effective, why do we need to wait for policy and regulation? And shouldn't engineers be knocking on CEOs' doors? And that's kind of an interesting one, because I can't say who it is, but I'm currently working with an organization in Norway who is actually doing just that. They have a methane solution, and they are actually knocking down CEOs' doors, which is good. Second one is, how effective are existing methods of detecting and repairing leakages with natural gas pipelines, and how good are we at detecting at the moment? And the third one, which I thought was quite interesting, maybe a nice one just to end on. If methane is so bad, is there actually a net benefit from using it as a fuel, capturing it and burning it? And so I'll let you figure out how you answer those three. And sorry, everybody, but those will probably be the last questions we take. Time.
Okay, so the first one, absolutely. I think it's incumbent upon us as engineers, to be advocates for net zero more broadly and adaptation more broadly, but methane reduction in particular. As I pointed out in the talk, there's a huge number of benefits to be gained rapidly from methane mitigation, and we should certainly be knocking on the senior management team's door to say, that this is a significant opportunity for our business, not only in terms of reducing those leakages and providing more product, but in terms of possibly using that methane and utilizing it in various industrial processes. So that's definitely the case. It would be helpful if policymakers and governments could assist us on that journey, but for many cases and many of the opportunities, we could do that right away. The second point, which was around how effective our current technologies and processes. Many of them are, fully understood and are very effective. I think what's been missing has been the awareness of the issue in terms of its broader impact and the contribution it could make to climate change mitigation. But increasingly in an increasingly energy tight world that is trying to transition, it makes perfect sense to perform those repairs to tighten up the system and to ensure more product gets through to market. And it is important, gas, methane as a fuel is going to be needed for some time to come to support the energy transition. I mean, we're seeing the impact all over the world today of what gas shortages can lead to. Into gas reduction, methane reduction, methane use reduction is important in the longer term, but over the near term, we need to make that transition, as we said, effectively and justly, and that product has value, and we should be using that product rather than letting it escape to the atmosphere. So that's and in many cases, particularly if you look at things like agricultural manure wastes, tackling those actually leads to negative emissions outcomes that can be used as offsets against net zero. So there's even greater benefits to be gained by tackling that livestock manure sector. So yeah, I think that hopefully that adequately answers that suite of questions.
Yeah, very good. Thank you very much. Well, apologies to anybody whose question wasn't answered. There are quite a few, but we're about 8 minutes over, so I'm going to have to close in just a moment. The questions will be available to Tim after the event, so at least you get to see them and maybe choose to respond to them in some method, and or maybe that'll inform some future thinking. I'm not sure if we can respond individually. I think GDPR might prevent us from responding to individuals, so sorry about that. But the fact we've run over is a good sign. Means there was a lot of interest. I just want to thank you, Dr. Fox, for a very engaging, very informative, and very entertaining sort of delivery. And thank everybody for your attendance. And here we'll close the webinar. Thank you, everyone.
Thank you.